Hello, this is Nathan Diltz, and I'm going to be doing my physics experiment today for Dr. Shane Schulteis' class. Today we'll be going over Galileo's uniform acceleration theory. This experiment and Galileo's subsequent experiments and mind experiments were important to helping him unravel the motion of celestial bodies and begin to mesh it with other contemporary scientists of the time who were making discoveries into the nature and orbits of the Earth in relation to other celestial spheres and bodies. Originally, Aristotle believed and taught that if you had two objects, one being heavier than the other, and they were dropped, the heavier one would hit first. While this anecdotally seems to make sense and was the prevailing logic for about 1,000 years, Galileo came up with some thought experiments that came to contradicting conclusions. He started in his mind's eye thinking about, well, what if you had two rocks that were roughly this similar size but different weight, and they were dropped together? And he asked himself, what if they were tied together with a rope or a cord? Would the lighter one drag on the heavier one as they fell? As he began to think about these kinds of things, he realized that Aristotle's hypothesis was incomplete. Biographer and student of Galileo, Vincenzo Vivini, recorded in his biography of his mentor Galileo that he had taken two objects to the top of the Leaning Tower of Pisa and dropped them from that height to verify his theory on uniform acceleration of masses. And of course, historians have not been able to corroborate Vincenzo's account. However, we do know that Galileo did roll objects of different weights but similar sizes down a slope, and this allowed him greater control and accuracy in recording the outcome of his experiment. But since we like a good show, we're going to follow Vincenzo's account, and we're going to simply drop objects from a height and record whether or not they hit at roughly the same time and see if Galileo's thought experiment is true. We'll also try to determine how fast they do accelerate. We know that Earth's gravitational pull is roughly 32 feet per second, and so we will be recording the amount of time in the seconds that it takes for the objects to fall and try to calculate roughly how fast they are falling. As you can see, we have our two objects. They're roughly similar size, but they're dramatically different weights. This Chinese meditation ball is considerably heavier than this paper ball. We are going to elevate them to a height of 7 feet, and we're going to release them simultaneously and determine whether or not they hit the ground at the same time. Like any good scientist, we're going to have a control in our experiment. Our first run, we're going to drop these two metal spheres that are exact same weight and height together to make sure they hit at the same time. Then we can switch out for the paper and the metal spheroid and see if there's a difference. Chrome spheroid drop 7 feet.
Ready, set, go. Go.
Chrome drop and spheroid drop at 7 feet.
Ready, set, go. Go. Go.
For kicks and giggles, we're going to try different sizes and weight, just to see what happens. As you can see from our experiment and its results, Galileo and his theory and hypothesis have proven correct. Objects of different weights do fall at a uniform or accelerate at a uniform speed. This experiment, of course, isn't perfect because we have an atmosphere and we have air circulation and friction and things that dilute the results, but the experiment, serves its purpose. This would be a more perfect experiment if we could get exact objects of exact same size and drastically different weight, and if it were conducted in a vacuum. We aren't able to do that, but this will do. Now it's time to do the numbers. Here we go. We've got a list of our different items and the record of how fast they fill. And we decided to go ahead, since we showed from the film that they both hit roughly at the identical time. We decided to take an average for all of our objects that were used in our acceleration experiment. The average for all of our objects falling for a distance of 7 feet was 0.692 seconds. Now, for us to determine velocity, we take the distance and divide it by the time. And so we take our 7 feet divided by 0.692 seconds, and we came up with approximately 10.1 feet per second. We decided to check our numbers by comparing it against established science. We have the formula for the distance of a falling object, and we took that distance being equal to 1/2 the Earth's gravitational constant multiplied by the time squared. And we moved that formula around to suit the data we had. So we decided to have the distance divided by the time squared multiplied by 2 is equal to gravitational constant. We know what the Earth's gravitational constant is, and we wanted to see how our results compared. Well, when we plugged those numbers in, took 7 feet, divided it by 0.692 seconds squared, we got 14.6. Multiply that by 2, which is 29.2 feet per second. And that we compared against what is the known gravitational pull of the Earth. A should be 32 feet per second. So it wasn't exactly on, but it was close, which showed us that our experiment, well, it wasn't precise is what it showed us. Honestly, there were a lot of variables. It was a rudimentary experiment, but there were so many variables involved. The stopwatch, accuracy, my release accuracy, the distance accuracy. There were a lot of variables involved. And one thing that this did demonstrate is Galileo was really smart to perform this experiment on a slope, because it would have been a lot easier for him to measure and for him to more precisely carry out his experiment by doing that. So goodbye Leaning Tower of Pisa, and hello slope and a bunch of different spheroids being rolled down them. I'm Nathan Diltz, signing off for this week's Science Studies with Schultheis. Next week, we'll be covering Stephen Hawking's A Brief History in Time. Chrome spheroid versus the blue knitting needle of Grandma's destiny. Like any good science experiment, you have to start with a control. And so we're going to take these two identical balls